other one as well. And Anthony, Mark, let's see, we had Logan, Coin, Mario. How you guys doing? Mark, Anthony, Bautista, Jason Bitzargan, Michael Higgins, Anthony. Okay, that's that. Oh, and Caesar, right, of course. Great. And what did I do? Somehow I maximized the window. I didn't mean to do that. Okay, that was easy. All right, so yes. Yes, in fact, I was just going to comment on that. So let's go to the agenda, which is under discussions. I don't have it yet, do I? So I'm going to say new discussion. I'm going to say today is 5/13 is the 13th day of the 5th month in the 20th year. And that's it was 2 months ago today that Corona taught the band to play a new tune. Let's see, what do we got? Okay, so today's agenda, and I think the first item will be to talk about the midterm part 2. And so let me say this about that since we're there. It's just about done. In fact, for all intents and purposes, it's done. An idea came to me at the end, which was I should add a little essay to each question for you to comment on how you like that question. So I can get a little metadata, some feedback about, and why you answered what you did, and maybe, argue that your answer is just fine. And why aren't you getting full credit and that sort of thing. So, and I think the timeline for this will be, so I think there's 5 questions. The first 4 are sort of a combination of multiple choice and multi-answer, right? Where a multi-answer, where you have more than one possible choice being correct, you check the ones you think are right and don't check the ones that aren't right. I don't think I have any fill in the blank. I need to have more of those. Those are a little bit tough. The trick there is to use regex, like a regular expression feature of MyOpenMath, which will sort of blur over words that capital letters, lowercase letters don't matter, and ending of words, misspellings, that kind of thing. So it allows you to give correct credit for a more wide variety of answer possibilities. But I think, like I say, there's 5 questions. The first 4 being these matching multiple choice combinations. Some of them have more than one in the same question because they're relating to the same thing, or same idea. And they're mostly relating to inheritance and that sort of thing, classes and class inheritance, polymorphism. But the last question is a programming prompt where I give you a complete and working program and ask you to modify it. So in the complete and working program, I'm using the vector class, the vector standard template library type, and I want you to get rid of that sort of like retrograde, which is kind of what we do in the text, right? When we go into chapter 17, 18, 19, we're saying, okay, in 7a and the first part of 7b, we use the vector class happily with abandon, but it's one of the themes of this text where it's depth first, right? So dive down deep and use this vector object, which you don't know a lot about how it works, but you know how to use it in context. You know its member functions, basically, and how to use those. You don't know necessarily all the details about how they're built, right? That's what you're getting in 17, 18, 19, right? All the details on how the vector class is built. And so what I want you to do is allocate memory on the heap instead of using a vector. So you're just going to build a new class, and everywhere you see vector, use that class instead. And that class is going to be a board. So maybe can I do a little drawing here? Do we have the paint box open? I just sort of want to describe some of the details of that. So let me see. Is this a thing? Yeah. Okay. I think it is. Yes. I did. Yeah. Sure. So what's happening here is it's going to be like a Sudoku. Have you played Sudoku? Oh. Well, let's take a quick gander into Sudoku. So for that, I start out every day on the New York Times crossword. It doesn't take me very long because I've been doing this so long. Look at my current streak, 196. Right, so that's the number of consecutive days I've done the puzzle without missing one. Now, I had the flu like 197 days ago, something like that. Actually, I think I had a busy day, and because I had the flu in late August. It's like just flex days and stuff before the semester started, and I don't know, 196 days. Anyway, yeah, that was August. And this is May, so that was like, oh yeah, see, that was like more than 196 days ago. In any case, that was the fall semester. And so my longest stretch. Anyway, let's go down here to, so they have all kinds of games. Some of them you can play for free. To use the puzzle, you have to have a subscription. But I think somebody like Sudoku here, I think that's free, right? Yeah, it does say free on it, right? And so if you haven't played Sudoku, I recommend it as a productive way of building your deductive reasoning powers. So this is a fairly easy one, I think. It's sort of an interesting business. So it's a Latin square, meaning that all the numbers 1 through 9 appear in every row and every column. So the numbers you've got here are the clues, right? So you have to be given a certain number of values in order to specify a particular configuration of row and column 1 through 9s, right? So what are we missing in the first row? Well, 1, 2, 3, 4, 5, 6, 7, 8 are missing, right? So we look in this column, we say, oh, look, there's 6 and 7. So we can't have 6 and 7 in this first column. So this must be an 8, right? You see that deduction there? And so these are either 6 or, well, that can't be a 6 because there's a 6 down here, right? So this must be the 7. And this must be, oh, yeah, the 6, right? Okay. All right, so we got the first row. And in every 3 by 3 box, you also have all the numbers 1 through 9, right? So in the first box, we have 1, 2, 3, 4, 5, 6, 7. So we're missing 3, 4, 5, 9, right? And you can kind of, it's basically a process of elimination. And I seem to recall writing a solver for this, so I got to the point where it was you just follow an algorithm, and so it becomes sort of trivial solving these things, and I got bored with Sudoku at some point. Although I went to a mathematics conference once where one of the themes was Sudoku, because it's heavily mathematical thing. And yeah, if you go to Numberphile and look up Sudoku, you'll see they have a recently proved result that the minimum number of clues you need to specify a particular Sudoku board is 17. So it's yet another instance. If any of you know Professor Matthews, he's on sabbatical this term, so you may not have run across him, but he has a fascination with the number 17. So it's just more confirmation for him that this is a crazy number. There's also a number of wallpaper patterns is 17, if you ever get to that. All right. Let's see, what am I looking at here? So do we need to finish this? No, we don't. But look at this middle column, right? So we're missing 1, 2, 3, 4, 5, and 2 and 5, huh? So this has got to be the 5, right? Because there's a 2 in this row, and this has got to be the 2, right? And what? So now there's only 1 missing in this block here, right? So it's got to be a 1, all right? And then what do we got over here? Well, this one, there's only 3 missing in this row. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 4, 5, 4, 8, 9, I mean to say. So 4, 8, 9. So this has got to be a 4 or 5, and this has got to be a 4, right? 4, 8, 9, and there's a 5. Sorry. Oh, this could be an 8, right? Could this 4, 8, 9, I said? Okay. So, oh, and this can't be an 8 because there's an 8 here. And it can't be 9 because there's a 9 here, so it's got to be a 4. Okay, so 8, 9, right? Like this can't be an 8, so it must be a 9. This must then be the 8. And so we could go ahead and finish this, but I don't think we have time for that sort of thing. But you get the idea that there's this pattern of rows and columns, all with the same number of things, and each box of 9, each 3 by 3 box must have the same number of things, right? Okay, so going back to where we were and getting back to the drawing pad here, if we have a 9 by 9, is this, I'm going to try to draw here. So I'm not going to make the full 9 by 9 grid. I'm going to make a 3 by 3 grid, and imagine each one of these cells is another 3 by 3 grid, right? So this is not Sudoku, but it's kind of like Sudoku. You might call it night Sudoku. And so what you're going to have here is an arrangement of knights. So we're like the chessboard piece, a knight. By the way, this was inspired by watching Knuth's last Christmas lecture. This is Donald Knuth, the professor emeritus at Stanford, who wrote The Art of Computer Science. 4-volume set with multiple editions of each one. I think I don't know I think there's 4A and 4B maybe. So there's 2 versions of 4. But I think there's a lot of game playing in there, and so he introduces this idea of night Sudoku, where so you put 3 knights in each one of these 9 squares, right? And the idea is that there have to be 3 knights in every column, and 3 knights in every row, and 3 knights in every 3 by 3. Yeah. So let's maybe I'm just going to sort of fake it here. So there's 1 here, 1 here, and 1 here. Let's say you see those are in different rows and columns, right? And then this one is maybe here, here, and here. And then 1 in this, so this could be like here, here, and here. Is that clear enough? It's a little bit abstract here, but all right. So there's 3 in every row on the first 3 rows, and so we go to and there's 3 in each 3 by 3 box, right? So then what would you do here? Maybe put 1 here. That's a knight. These are all knights, these little dots. Okay. And maybe this is the second row. Yeah. And all right, so now there's 3 in every row in the 6 rows 4, 5, and 6. And I can finish it up down here, right? So the question is, if these are knights, then for each knight, how many knights are attacking that knight? Like, so right here, how many knights are attacking this one? Well, this one is attacking it, and that one is attacking it. And when you look at knights, I don't know. If you think about, do you know how a knight moves? Like a little L-shaped thing on the chessboard. So it goes 1 up and 2 over, or 2 up and 1 over, right? That kind of an L shape. Or it could go 2 up and 1 to the left, or 1 to the right, either way, right? And so if you think about a knight, it's got 8 places. A knight in the middle of the chessboard has 8 different places it can move to, right? There's the 2 in the upper left, 2 in the upper right, well, how am I thinking about this? So you can go L like, yeah. So there's, yeah, 2 in the upper left, 2 in the upper right, 2 in the lower left, and 2 in the lower right. Gives you 8 possible moves, right? So the largest number you're going to see is an 8. That's if, and I don't know if that's even possible. Is it possible to have a knight? I think it is, right? How could we set that up? I'm going to take these guys off and try to set up a situation where, so this and this would both attack this guy, right? And so would this, sorry, that's a little bit sloppy, and that, and so would this, and this, and so would this, and this, and that's still following our Sudoku rules, right? Where I guess we'd need another one like up here, and here, and I guess we're here, huh? Right, and so these first 4 squares, you can see this guy here would be hit by 8 different knights, right? So if there's a knight on a square, then you want to count the number of knights that are attacking that knight. Or maybe they're just friendly, hello, knight. It's not necessarily an attack, it's just a neighbor, a neighborly wave. Hi, knight. So the first thing is that your board will generate a random knight Sudoku, right? So a random arrangement of knight Sudoku position. And then the next part of your program will replace each knight by the number, which is the number of knights that are attacking that knight. All right, and that's already written for you. So you can appreciate how it works as you go, but and maybe improve upon it. I'm not saying it's the best code ever written, but it does use the vector class, right? And so that's going to be your programming challenge. Is that clear enough? All right. If you have questions about it, so the timeline for this, I think what I'll say is, it should be in Monday at 2. How about that? So I should have it ready shortly after class. The only thing that's left to do is to replace all the vector instances with, is to write a class that will do this part of the vector. That actually it should be one class that handles a board array, right? So an array in rows and columns. So like a pointer to a pointer would be a good thing. I think that's one thing we'll look at today is how do you make a matrix class, for instance, right? All right. A matrix being an arrangement of numbers in rows and columns. Some of you are in linear algebra this term, right? So let me get the chat thing going here. I see there's a couple of remarks in the yeah, okay. And so there was another, are we doing the midterm part 2 today? Yeah, right, and it will be assigned today. I think I must have answered that question then. So and it's just not quite ready yet. I had this idea that it was ready, and then I had this idea that I wanted to add this essay box for you to make commentary, so I can, get some feedback from you, and give you a chance to justify your answer if you feel like you have been unjustly marked down. All right, and I will read all that. So let's see, what else? So chapter 19 is also on the docket. Okay, and then that'll kind of wrap it up for this term. In terms of the lecture portion, class meetings, and then so the final exam, I think as we said last time, is Wednesday. Today is the 13th, so that'll be the 20th at 2 to 4 p.m. And I guess we'll try to stick to the window, the time window. I guess partly because, so the midterm, you've got a lot more time. The final exam, I'll try to make it fairly short. I should know better than to ever promise that it's going to be easy. No, I won't promise that. But I'll try to cover, most of the key ideas and give you an opportunity to show what you know, and not belabor things too long because, uh, you know, whatever. It's under unusual. It's been an unusual semester. I've been teaching a long time. I don't think I've ever had such an unusual semester as this. I was teaching September of 2001. I had an 8 a.m. class, and so on September 11th, I remember seeing on TV. That's when I still watched TV. I don't watch TV anymore. This is because you see this kind of shit. Uh, but the disaster in Manhattan, and then arriving in class, trying to teach like everything was normal, which clearly was not. Especially became apparent when one of my better students, well, all of my students are my better students, but a gentleman stood up who I knew was a dog trainer and said that he's just gotten a message on his phone saying he was to fly to New York City with his dogs. It's the last I ever heard of him. I hope he's all right. So again, the sort of epicenter of strangeness is Manhattan. I don't know. What is it about Manhattan? It's an island. It's a drink. It's a canal. No, that's that's something else. That's Panama. Although it's got canal-like waterways, doesn't it? Anyway, all right. So there's that. So are we ready? Any comments about anything? It won't also be no, it won't be due today. Yeah, like I said, the midterm will be due Monday, and I think partly that's because I don't know what everybody's schedule is, but give you some leeway there. And I guess final exams start on Monday, and then I also want to sort of limit that to that time frame because that's when I know you're not responsible for being in the other exam because that's the way the final exam schedule is set up. So. All right. Yeah. All right. Good. So let's then save this and publish it, and maybe go to the discussions just to move it into a place where we can easily get to it. Right. So pin it to the top, which is not on the bottom. To my way of thinking, this is the top. All right. And we can open that up again there. All right. So let's then zip over here to the text where we're in the wrong chapter for some reason. Ready? And Chapter 19. All right, so changing size, templates, right? So this is why I wanted to just sort of jump to chapter 19. I know we didn't do a proper job of solving all the problems in chapter 18, but you can maybe take them. I mean, this book is designed for self-study, so you can be an autodidact, as they say. That's somebody who teaches themselves. And so many computer scientists are now. There's a lot of people, with productive work in computer science who just, skip the whole college thing. Maybe I shouldn't say that. But it's good to have the difference is that if you have a college degree, then you get to be a manager. And then you don't have to program anymore. I told you the story about the recruiter in college who asked me, "How do you like computer?" I was interviewing for a programming job. He says, "How do you like programming?" Well, it's kind of like washing the dishes. Somebody's got to do it. Yeah. I didn't get that job, needless to say. I'm not very good at interviews. I don't know. It's some kind of Tourette's problem. I can't explain it. All right. So back over here. So shall we? So do we have a quote? Success is never final. Uh huh. Um, Winston Churchill. Well, yeah. Um, at the end of chapter 18, we had our vector. We could create vectors, we could copy vectors, we could rely on them to correctly release their memory when they go out of scope, and we can access vector elements using the subscript notation, right? And that's all good, but how do we change the size of a vector? So we want to be able to resize it. How do we catch and report out of range vector element access? Right. So we haven't talked. Have we ever talked about the the at member function? It's the word at. So if you do vector dot at and then give it an index, that is the same as the subscript operator, except it does range checking. Right. It checks to see, is this actually, something that you've allocated and initialized memory for. All right. So, for example, how do we define a vector so that, so we have the template thing going on, and we can, well, do pushback, right? I don't think we have pushback yet, right? And so, especially if it grows, right? We do, well, of course, yeah, it's going to grow when we do pushback, right? So, actually, the size will grow, but the capacity will not necessarily grow. The capacity is at least as big as the size, but usually bigger. So the idea is you allocate more than you are actually going to use, and then if you do enough pushbacks to where you run out of allocated memory in your capacity, then you reallocate. Which is a big operation, obviously, because you have to create a whole new section. Maybe use move semantics for that. Yeah. I didn't put move semantics on the midterm. Maybe I'll have to find some questions for I haven't written the file yet, so give me some ideas. Yeah, send me an email. So what else do we got here? There's another template and resize, right? So perhaps you want to resize your vector with that member function, which we know we have this member function. I don't know, we haven't used it that often, but it's there, right? I'll tell you what, I'm not sure that I have the chapter 19 stuff here, so whoops, where am I? I'm in a balloon. Oh, I don't want that. Okay. Which you can't see what I don't want, so sorry. Let's see, I want to go to my directory where things are, and I guess go here and say, go back and go down there and there. Oh, I think it's actually back over here. I was in the right place in the first place. Programming code, chapter 19. I don't think I have this in my directory where I'm putting all my eggs in this big basket. All right, so I guess I want that. All right, yeah, that's everything. All right, so I'm going to copy that, and let's see, where am I? I'm here. I'm going to say open folder in Explorer. And yeah, oh, I do have chapter. Oh, idiot. Okay, I didn't need to do that. Okay, so with that, let's let's read a little further here. It's nice and useful to have vectors that allow all this, but why is it important? I think we talked about this last time, so let's skip over that. And the last sentence here says the obvious exception is the phone. It is a computer. Sorry, we don't have the context of this. And when I look for the numbers on it, I'm looking for the output of the program just like we're writing, just like the ones we're writing. In fact, those numbers may very well, okay, never mind. Obviously, not all containers have the same number of elements. Could we live with a vector that has its size fixed by its initial definition? Yeah, but then it would be, you'd put the onus on the programmer every time they want to change things to change them, right? I think we kind of read through that. So let's skip on to 19.2, changing size, and maybe bring up, I don't know, maybe we did this. I can't remember what we've done. But I'm going to bring up, so I'm going to go to the code window. And I need to change which code window I'm looking at. So not that one, but maybe this one? Oh, okay, so that is not associated with the current window, so I'm going to have to say, yeah, I think that's it, huh? Okay, so I'm going to say add existing item 19.2, I believe that should be the correct 19.2.1. All right. So what do we see here? We have a new thing called space. Well, as I like to say about computer science, it's all about memory. And where's the memory live? It lives in a space. Yeah, it's all about time and space. Number of elements plus free space slots for new elements. All right. So I think we're going to end up calling this capacity instead of space, but we're just getting started. This is our first draft on this, right? So here's the constructor, and it's allocating the null pointer. Well, 0 for size. A lem, I guess that's the null pointer, and space is an int, so that's also interesting, huh? So this should actually say null pointer, because that way you avoid the confusion of 0 being more than one thing at a time, right? Null pointer is clearly just null pointer. Okay, and so I don't think this is not something we can actually. Can we execute this thing? So we have yeah, the constructor is defined here, right? And then we're creating an object of this type, and let's see if it does it even compile. Will it blend? Yes, it does. And we can see that it produces this incredible output. Yeah. So all of that is good. So it's sort of a shell, though, right? So let's put that fish back in the sea, and get the next fish in the queue, the fish queue. And I'm going to say no, existing item. God, 19.2.2. All right. And here we have that same beginning, but now we have a public section where we have a default constructor without a definition. We have a function called reserve, which is going to allocate new memory, and a function called capacity, which returns an int, which is the capacity, right? So this reserve is what's going to reallocate. Well, I guess it's going to have to copy over. Should we see how it works? Okay, so we still have space as a private data member, right? And we have the definition of our default constructor here. Again, this should be null pointer, right? But these are ints, right? And then in our function, we declare v to be a vector. We assign reserve with a value of 10, and we return capacity. What does reserve do? Do we have it? Oh, here it is. Okay, right. So reserve takes an integer called new alloc, and if new alloc is less than space, right? So that means that we want to increase the allocation. but oh, sorry. If new alloc is less than, so if we already have enough memory, because new alloc is less than or equal to space, then we're just going to return because we never decrease allocation. Is that true of the vector class? What if you resize for a smaller vector? What happens? I don't know. Have we tried it? Maybe we should try it. How would you know, right? Well, I suppose we could do a little experiment. Can we do that experiment here? We've got this vector. How about this? I'm going to change every instance of vector. I'm going to do a Control H here, and every time I see vector, I'm going to write instead VCTOR, not to be confused with Victor. And replace all. 7 occurrences. Okay. So then I can include vector, and using namespace standard. Why not? Being lazy. Okay. So does this run, first of all? I guess, let's see. Oh, well, we haven't talked about what reserve does, right? So it allocates memory on the heap, right? So it creates, this is an array of doubles of this new alloc size. This is if new alloc is bigger than space, right? So we need to allocate new space. And we do that on the heap. And then we initialize, we copy the old elements, right, to our newly allocated space, and we delete the old elements, and then this variable p, which is the address of this, the first element of this newly allocated space, is where we're going to put, so we assign that pointer to a lem, right? Because a lem now is going to point to this newly allocated region of memory, and then we reset space to, yeah. So that's kind of it, right? That's how you do it. That's how you, well, it's one way. It's certainly a way of doing what we want to do, right? Which is to allocate new memory, copy the old data into our new memory, delete the old memory, and then associate our variable, our member variables with these new values. So this is going to return from main, isn't it? So before we do, well, let's just do that and see what we get. Just, will it compile? Yes, it will. And notice that in the output here, it says exited with code 10, right? Because that is the return value. Y10, did we look at Y10? Because that's what that was the new memory we reserved, right? So then the new capacity is 10. Originally, it has what, 0, right? So we should we include? We should probably have some. It's funny. Why is vector in that brown shade? I wonder. I don't know. Oh, because it's. I should get rid of my find and replace, right? Let's go ahead and include IO stream so that we can output some stuff here, right? So, so I'm going to see out again v.size. Oh, maybe I should say what I'm seeing out. Okay, so this is going to be v.size equals v.size, and can we also do it for the space? Oh, it doesn't have a size function? Our vector does not have a size function. Okay, so we'll need to put one in, right? So it's going to return an int size, and we'll just define it right here, right? Return size. Okay, so that should work now. Where are we? Down here. Okay, and I think we have to do this. Well, oh, I think, yeah. Can I just see out v dot capacity equals. I think this is a public variable. V dot capacity. So run that again, and it doesn't like that. V dot capacity. Oh, it's a function. I'll say. Do we define it? So I'm scrolling around here. Well, it was able to return 10 to the caller, which was the console. But I guess that's funny because we. Okay, so let's. Yeah, I guess we can do it this way, right? All right. And capacity is a member variable which how does it get set? That it looks like space is set to 10. I don't know. Let's see what happens. Okay. So we get size is 0 and capacity is 0 because it's an empty vector, right? And those are the default values. I suppose we could try dereferencing the LM. No! Undefined behavior. Never dereference a null pointer. Okay. Or always check that it's a null pointer or not before dereferencing any pointer. Is the moral of that story. Yeah, so I'm sort of reminded of our doubly linked list. Well, you guys are working on that tree thing, right? And so you'll get plenty of opportunity to show what you know in that project about building data structures, right, from scratch. Okay. Is this course going to end on 5/20/20 like normal? My answer to that is no, because I promised that I would give you some extra time, and I'm going to stick to that promise. So we're going to go an extra week for you to turn in your work. If you finished on time, great. Glad to have you be done. But if you need some extra time, I get that. So, yeah. Will there be more? Oh, no more lectures. Although office hours are fine. So, if everybody wants to get together for office hours, yeah. And I don't know. It's kind of a busy week next week, honestly. There's a bunch of sort of college business I have to attend to, including hiring a computer science faculty member. Which we've interviewed a number, and we decided to interview some more. So that's an ongoing process, which is rather time-consuming. And then there's also, being president of the union. There's all this crap I got to do. But yeah, so but yeah, I'm going for another week. So if you look at the calendar, do we have a calendar? I suppose we can go to the browser and look at where's my browser? There it is. I think there's a calendar here, isn't there? Oh, just maybe did I take the calendar off? Looks like I did. Unless I'm blind. By the way, this Office 365, I finally realized if I want to show you a Word document or any sort of Office document, this is the ticket here. But yeah, I kind of realized that too late. All right, I knew it at one point and then forgot. I was trying to just share a window, which was an Office document through OBS. That just doesn't work. It's some sort of proprietary thing with Microsoft. But yeah, if I look at my calendar, you have a calendar you can look at. So yeah, I'm thinking we can go to like to the 29th, so right up to the end of May. And if that's still not enough time, let me know. I'll keep it open a little longer. I think I don't know. Do you need priority? Do you need to have a record of this class for your next priority registration? I noticed that Cal State went completely online today. That was the news I heard. So that includes Cal Poly Pomona. One of my favorite Cal States because the acronym is CPP, C++. So, yeah, I don't know. I'll try to keep up with my emails. I know I probably fell a little bit behind there. Um, Trying to stay ahead of things, which means not looking back. Oh yeah, there's a trail of wrecked train cars. Never mind. The train wreck is pulling into the station. Time moves inexorably forward, unless you're a physicist, in which case you can go sideways. Or even backwards, I think. I don't know. There is no time in physics. At least not. It's not really built into the fabric of basic physics. It turns out it's a weird thing, huh? So time is an illusion of our brains. It's like a biological thing more than a physical thing. Yeah, I don't know. People are doing studying anyway. I'm going off on a tangent. All right, so yeah, right. So plenty of office hours times. I did so as scheduled. I don't know. How about oh God, Tuesday is busy. Yeah, there's like completing meetings all day long. Um, well, I'll make an announcement when I'm free, um, and maybe class time on Monday would be good, right? That'd be a good time for office hours. So we just like have a regular um, time to chat. Maybe uh, it can be more you talking and less me talking, but we can have dialogue anyway. So yeah, answer that question. Now, where were we? We were looking at code. Oh, and I was going to do a little experiment, right? Where is that? Um, oh, which was okay. So when I run this, so did we see? Yeah, we saw 0, 0. Okay. So now what if so now I've got vector available, right? So I'm just doing a little experiment here. So I'm going to create a vector of whatever, int, and what do I call it? Vi. And so that's going to be an empty vector, right? So if I say vi dot, I get a context menu, which you can't see, right? But this sort of gives you an idea of the various, I mean, if you're doing it on your own, you can see it, right? It's got pushback. Are these in alphabetical order? No. It's got pushback, size, begin, clear, assign, and the first four are pushback, size, begin, and clear. I'll have a little star next to them, which is IntelliCode suggestion based on this context. So these are prioritized as, yeah, if you're going to do something with VI at this stage, probably one of those first four things, right? Pushback, size, begin, or clear. So how about size? But there's also a sign, there's at, there's back, there's begin, there's capacity, right? C begin, which is a constant iterator to the beginning. C end is a constant iterator to the end. There's clear, there's CR begin, a constant reference to the beginning, and CR end, right? So these iterators have modifiers. In place, yeah, anybody? Empty, end, erase. So these are in alphabetical order. Front, get allocator, insert, max size, operators, Resize is in there, swap, and then there are some underscore operators. Okay, but so I'm going to say, well, how about cout vi.size equals vi.size, like that. Oh, still need to complete my, oh, what am I doing? I don't know. And a little end line maybe, and cout vi.capacity equals vi.capacity. So, you know, what is the size of an empty vector? Well, that should be 0. What is the capacity of an empty? How come it's, I'm missing the stream operator. And then I'd like to vi.resize, and I think it takes an yeah, so should we say 10? And then repeat those two things. After, okay, I think that's all I want to do for now. I'm not seeing VI. Oh, I think it's because I returned already, right? Yeah. I need to get rid of that return, which was here, right? So I can cout instead, right? Maybe with an end line. I'm not going to bother with the fancy. Okay, so 10, right, was that size. Okay, so when I set this new size, then that's also the capacity, right? But let's do this. Let's write a little loop here for int I equals 0, I less than, oh, let's say 9. Okay, increment I, and then I'm going to vi.pushback I. Oh, I'm going to do that, but I'm also going to do these things again, right? Oh, we need to push back I. All right, so in a little loop, let's see what happens here. So you see, originally it's an empty vector with 0 size and 0 capacity. I resize to 10. I do a pushback, and the size goes to 11. Right, but that was bigger than the capacity, so it's resized. So the capacity grew by 5. Why 5? I don't know. It's the way the thing is built. This decides, well, I'm not going to do it again until I get to what, the 6th one, in which case I'm going to resize it to 22, right? So the size is then 17, but the capacity is 22, right? So you see that the size and capacity, so it doesn't, because, you know, resizing or reallocating, I should say, is such an expensive operation. It wants to minimize the number of times it does that. But now let's see what happens if I make it smaller. So how do you make it smaller? Well, there's erase. Oh, let me get back to the code. There's erase, right? So I'm going to do another for loop like this one. And I'm going to say, and erase will actually delete from the middle if you want it to. Generally speaking, that's to be avoided. Why? Well, if you erase something from the middle of a vector, then it's got to move everything to the right of it. Each one of them has got to be moved back a notch, right? So that's a lot of operations, which maybe maybe there's a better way, right? Well, a linked list is a better way, right? Because then you can just tie together your pointers from the one before to the one after, and then you don't have to move everything. You just move a couple of pointers, right? The downside being that it's harder to access an interior element when you do that, right? All right. So we got. I'm going to say. I don't know. Should we? Let's erase from the end. So I'm going to say vi dot erase, and I'm going to say. I think it takes a pointer, doesn't it? What does it say? Yeah, it takes an iterator, right? So I'm going to say vi dot end. -1. That's okay. So I'm subtracting 1 from a pointer, so that's pointer arithmetic. So it's going to move back because end is the one actually past the end, right? So if I want to erase a currently existing element, and then I'm going to report these two things again, right? All right. All right. So we notice that. Oh, it's here where we start erasing things. So the size goes up to 19 here, right? And then it starts getting smaller. But notice the capacity hasn't changed. So we never make it smaller? Oh, really? Never? So the capacity stays where it is regardless of... so we have all this allocated memory, which we're not using. So I'm kind of curious. At what stage does it start to then say, oh, well... maybe we need to free up some of that memory. We're using all this memory that we're not actually needing. Yeah. So okay. So let's go. I don't know, another 19 here. Let's see if it stays the same. Yep, capacity. So we get down to size 0, and we're still at capacity 22. Right. So that sort of makes sense then. That what he says up here, never decrease allocation. Well, I don't know if the actual vector class behaves that way, but seems to. We'd probably need a more extreme test to be sure. Or to have a more confident conclusion there, but that looks like that. All right, so let's get back to our text. I don't know what have we missed here. So here you have the size, the pointer to the thing, and the capacity, which is sort of at the end, right? So this is free space, but it's uninitialized, right? Which raises another question. When I erase something, should we go back and test that? I'm curious about this, right? So I've erased every element, right? But I can still print them out, right? I'm not going to try to go too far into this, right? So let's say the first 4 elements. So this is... these are elements that have been erased, right? Are they actually erased? So vi of I. Let's put a little space here or something. All right. So I run that, and it doesn't cry out bloody murder yet, although I don't see anything. The output window seems to be empty. I don't see anything. Your thread executed with code 0. That seems odd. Let's try that again. Oh, okay. This time I get an error. There's a range error, right? Expression vector subscript out of range, right? So even though this is allocated memory, right? Our capacity is 22. Well, let me look at the output here. Our capacity is 22. When I try to use a subscript operator to print out what is at those memory locations, which oddly sometimes it works and sometimes it doesn't. You don't always get a range error. I think it depends upon your compiler in part. I think the GNU compiler doesn't give you a range error here. Is it good to get a range? I think it's probably good. I mean, why are you? That could lead to undefined behavior if you're trying to access uninitialized memory. It was initialized, but then it was erased, right? So, that's one of those cybersecurity issues, right? Was it really erased, or did you just, lose the address of it? Which clearly we have the address of it. So I guess I'll ignore. Maybe it's because I went all the way down to size 0. I don't know. But let's go back to our code and maybe move along here. Well, let's go back to the text. So, reserve and capacity, right? So this is actually what we've been looking at. And resize, I think we kind of looked at that. Given reserve, implementing resize for our vector is fairly simple. We have to handle several cases. The new size is larger than the old allocation. The size is larger than the old size, but smaller or equal to its old allocation. The new size is equal to the old size, and the new size is smaller than the old size, right? So, and I think this is kind of what we've got. Okay, yeah, reserve, and okay. So what cases do we need to consider test, right? I think, okay, so pushback. Are we ready for that? Let's jump to pushback. Otherwise we'll take forever with this, which we've already done. Here it is, 308. The grains of sand in the hourglass are becoming innumerable, which means countable. It sounds like uncountable. Maybe I should say numerable. There are myriad grains of sand. There are innumerable grains of sand. You can numerate them if they're innumerable. I don't know, whatever. So pushback, let's go to that. When we think about it, pushback may appear to be complicated to implement, but given reserve, it is quite simple. Okay, so this is 19.2.4. Let's put that on the chopping block, or on the test bench. So I'm going to go to code. I'm going to go exclude this from our current project. I'm going to add add existing item 19.2.4. Really? It looks like there's a lot of stuff in between here. Oh no, that's 19.3. Okay, so 19.2.4. Is this just what we were looking at? Oh no, this has got resize and pushback now, right? All right, so yeah, it has everything that we had before, the reserve with the new alloc, and it's still the same reserve function definition here. But now we've got resize, right? So what does resize do? Oh, it's here. Well, it calls reserve on new size, right? And then for all the elements up to new size, it initializes them to 0. And then it changes the size to new size. That's easy, because we got reserve, right? Reserve did sort of the heavy lifting here, which is allocating memory on the heap, deleting it, and then rejiggering your member variables, right? Then we've got pushback. Okay, so here's pushback. Can I get it to be all together here? It's a little easier if they don't waste there. I don't know why. It's just I don't like to read those blank lines. There's another one here, right? Who needs that? So the comment says increase vector size by 1, right? Because we're pushing back, so the size, so the number of elements we've initialized is 1 larger, right? And initialize the new element with this new value. And no more free space. Get more. So if space equals 0, then reserve 8. Why 8? Why not, right? So if you're pushing back onto an empty vector, then just make it 8. We noticed that our vector didn't do that. Wasn't it like 5 or something? So when we called pushback, it added 1 and then 4 more. 1 for the one that we have in, and then 4 more for additional space. Yeah, whatever, huh? This is doing a little better than that, or it's more profligate than that. It's using 8 instead of 4. If space equals size, right? So this is the case where we've used up all of our allocated memory. Then we have to reserve more. Oh, so now we're going to have twice the space. And this is not, as we saw, it's not exactly what our vector does, right? Although I seem to recall that I've seen this kind of behavior, where I mean, it is sort of the lore has it that this is how vectors work. As soon as you need to allocate more space, it doubles the allocated space, even if you're just pushing back one element, right? The idea is you need more, and memory is cheap. Yeah. What if your objects are very, very large, right? Then, like each one is the entire memory of a full computer. Yeah. Then you might want to be a little bit more careful. But this is doubling the allocated space, and it's setting it's initializing the new element at the end, and it's incrementing the size by 1. Shouldn't we change the capacity? Well, I think when we call reserve, that does that, right? Yeah, so the new space is the new alloc, right, which is going to be twice the old space. Okay, and then here's a little function that tests all that. And it's going to return capacity. So what is it doing? It's creating an empty vector, right? Then it's reserving 10, enough memory for 10 of our objects. And they're doubles in our case, right? And then it's going to resize to 4. So it's making it smaller, huh? So, I'm kind of curious at each stage what's going on here. So I'm going to say cout v dot. Do I have size? Capacity. I need a size function, right? Yeah, we had to do that for our previous example as well, right? So up here, I'm going to put in a little size function. So return size. Okay, so now back down here, I can say size. Okay. And should we kind of know. Oh, we don't have IO stream, huh? So I kind of want to see what's going on here, right? So let's just have oh, this should be a capacity here, right? I'm just going to do this here and here and here. Okay. Will that run? Will it blend? Yes, it will blend. And so this is size and capacity for our empty vector. When we called the let's see, can we look at the code here? Okay. And this is the wrong code. Excuse me a moment while I find the right code. I think we're here, huh? Yeah. All right. So this first two are 0 and 0, right? That's these two lines here. Then we reserve 10, and the size is 0, and the capacity is 10. So the reserve doesn't change the size, it just changes the capacity, right? When we resize to 4, then the capacity is still 10, but the size is now 4, right? And then when we push one on, the capacity is still 10, but the size is 5. This is what you'd expect. And then it's going to return the capacity, which is 10, which you don't see here. Okay. There, 10, right? Okay. Let's then press on. The big fool said to press on. And so there's a lot of discussion about that. You can read the... so here's our vector so far. We almost have a real vector of doubles. It's got size. It's got a pointer. This is not... it doesn't have correct style here. I guess this should be indented, huh? And then it's got a constructor. Oh, and then it's got an explicit. So have we talked about explicit? So we don't want implicit assignments. I think we did talk about that a little bit, right? Okay, so this is, I think, bringing up some stuff that was in chapter 18, where if you have a constructor, the copy is this the copy? So this is the default constructor. This is a constructor where we have S elements, right? But we don't want S to be an actual element, right? We want it to just do this, so it's not going to... What does the explicit mean? I suppose we could go to the... so here we are in chapter 19, section 9.2.6. And if we scoot down here to the glossary and look at explicit, is it here? It's not. Oh. 19.2.6, huh? So what if we go here and say find explicit? Oh yeah, explicit constructors, right? And find me the next explicit. A constructor defined explicit provides only the usual construction semantics and not the implicit conversions, right? So it's not going to implicitly convert this to the size of the vector, or to a vector element, right? So because we've disallowed that, right? To avoid surprising conversions, and we and the standard define vectors single argument constructors to be explicit. It's a pity that constructors are not explicit by default. If in doubt, make any constructor that can be invoked with a single argument. That's only if it's got a single argument. Yeah, maybe reread that section. In any case, let's press ahead and see that this is our 19.2.6. Shall we drop that on the chopping block here? And exclude this from the project. Bring in existing item 19.2.6, and let's see, so this has got all of those features, right? So notice this does not have the explicit modifier here, right? Right, so this is, sometimes the source code comes with the book, and the code in the book disagree, and this is one of those cases. So is this a problem? Well, I don't know. I haven't looked at main. What are we doing in main? This is the assignment operator overload, right? So it's sort of bringing everything so far together, right? The copy constructor, the assignment overload copy constructor, the I don't know, the pushback function, the resize function, the reserve function. This is the copy constructor. It's got a couple of overloads. This is the copy assignment, is what that's called, which is defined below, right? This is the destructor, which, this is, when it goes out of scope, it's going to call this, which is going to then automatically free up the memory. Okay. Should we run this and see? What does it do? So in main, we declare an empty vector. We reserve. So there's the same stuff, huh? Pushback 7. Then we create another vector A. Now here we're assigning A to V. Well, let's run this, and then I want to see, what about that explicit? I think explicit is not a trivial keyword. We're not seeing anything here. Okay, it's sort of just waiting for me to press. Right, because it. Oh, then it says return, right? But yeah, we might want to. I don't know, do we still have that in memory? No, on the clipboard, I mean. Yeah, which was what? Cout. Oh, do we have cout? No. Okay. So. I just want to, when I'm testing things, I like to, when in doubt, and I'm always in doubt, so I'm always cout. So let's see, cout v dot size, cout. Oh, we still don't have it. You have to keep doing this over and over again. Oh, maybe we do have size. Is that right? Yeah, here. Okay, great. And so v dot capacity. We're going to reserve new memory and do the same thing, right? Which I don't know, we've already done this, so I don't know why I'm doing it again. But here, let's do it here. For A now, right? A is now going to be a copy of V, right? Okay. All right, seems to work all right. And go to the output and take a look at the code that produces it. We see the empty vector here. Whoop. The empty vector here produces 0 size and capacity. We resize to 10, so the capacity is 10. What did I do there? Yeah, we reserve for not resize, but reserve 10. And then we call size resize with 4, which gives us that pushback. Okay, so at the end here is the new stuff, right? Which is that we copy. All right, so I just want to try this explicit thing. So if we go back to the code, and what if we say, v equals 4? Notice that doesn't cause a problem, right? I mean, IntelliSense is not complaining. And so what happens when we compile this? Oh, it's kind of stuck. Let me oh, okay, there it is. Okay, so notice, yeah. So what do we mean by v equals 4, right? We're in the code window, right? What was our intention there? Did we want a vector with 4 elements? Did we want it to be the vector with, element 4? What if we were to put a 4 here? I mean, in curly braces here, right? So let me close that other output window and try that again. Yeah, again, it's 4, right? So it doesn't think I've got a vector with one element whose value is 4. It thinks I've got a vector size 4, right? So the way to avoid that kind of confusion we talked about in chapter 18 is to, in the constructor, the copy constructor, the overloaded, where is it? So here's our vector class. This is the copy constructor. I think is it this one? I think it's in the copy assignment. I don't know. Where was that? Explicit, where it takes an int, right? Do we have, yeah, this one, right? So this is where the potential confusion is, right? So if we put the keyword explicit here, then when we try to compile this thing, it's going to complain. Yep, there's an error here. Copy list initialization of vector cannot use an explicit constructor, right? So then let's go down here and get rid of this, because that was just kind of weird. Actually, that one wasn't so weird, right? But we don't have a way of saying, oh, I've got a initiator list, I'm going to use that. So we haven't built that in yet, right? But if we get rid of that potential confusion, then everything works fine. Oh, except I don't have, okay, there it is. All right, so press on. Okay, questions, yeah. So that's the output, here's the code, here's strip. And we're just up on the break here, huh? So we're going to enter into template territory. So let's just get started talking about templates, and then we'll follow through on that. And this is sort of an important topic. I don't know why we didn't get to hear earlier. Live and learn, huh? Yeah, chapter 20 is actually pretty good too, but we're not going to get there. Okay, so, but we don't want vectors to be just doubles. We want them to freely specify the element type of our vectors. For example, we want a vector of doubles, a vector of ints, a vector of months. Okay, so I don't think we did chapter 9 the way it deserves to be done. I don't know why. What have we been doing all semester? Oh, we did some interesting problems. We did those n-body problems, which I've never done before in this class. So, was that too much physics, people? I'm sorry. I know, but everybody gets their chops in irregular ways, and that's not one size fits all the time. So, there you are. I know Coin was saying earlier, I mean, which you've been very forbearing. I appreciate that. That I've never had physics, and yeah, if you haven't, then Newton's laws are brand new to you potentially, right? But they're fairly intuitive, gravitational. Especially if you've ever fallen off a ladder. Gravity is a bitch. unless you want to put your teacup down and have it stay where you leave it. I suppose then it's not so bad. Okay, so yeah, all kinds. We want to have vectors of any kind of objects, as we've seen, right? So to do that, we must see how to define templates. A template is a mechanism that allows for a programmer to use types as parameters for a class or function. The compiler then generates a specific class of function when we later provide the specific types as arguments. So a template function is a function that doesn't get compiled at compile time. It gets compiled at runtime. And if you never instantiate one of these objects, you never get a template for it. So it never compiles that thing because you never used it. So template is just like it sounds. It's like a cutout, like an outline for here's how you make one of these things, right? With whatever type you've got. So you're going to have to generate new code. So it actually writes. It's like metaprogramming, right? It writes the code. It's code to write code. So the compiler at runtime. Is it the compiler? Yeah, it's something at runtime. Writes code to make an object of this type, all right, which is, say, a vector of ints or a vector of bools, right, as we've seen often enough, right? So let's take up with 19.3.1 after a short break. Any questions before the break? All right. Okay. All right. Yeah, you're talking about the physics, right? Okay, good. So I'm going to hit pause here and see you in 10 or so. All right. So let's see. Types as template parameters. Yeah. Oh, sorry. It took a little longer than I should have there. Yeah, email being what it is. Okay, so... So we have this output window here, and we want to make the element types a parameter to the vector. Okay, so here's what you do. You take this little keyword template, that's a keyword in C++, and then in the angle brackets here, you're going to, this is a general placeholder for what you will put in when you instantiate a particular instance of this vector type, template vector class, right? So we're just going to proceed, and everywhere we see what was our element, instead of a double, we put this T. So what is this keyword type name? It turns out type name is perfectly synonymous with class. The word class and the word type name mean exactly the same thing. So in fact, you can put the word class here. Now maybe I shouldn't say exactly the same thing, but for our purposes here, it might as well be exactly the same thing. I think there are some contexts where you can't use them interchangeably. For instance, I think if you're defining a class and you try to use the name type name, that won't work. But here, either class or type name will do exactly the same thing. And you'll see some people use class, some people use type name. Not to be confused with type def, which is another word that starts with type. Type def is when you're typically use it when you have a very complicated type name or object thing. You want to have a simpler name for the same thing. So you're just renaming a type. So type def is used to rename a type. Okay, so shall we get up 19.3.1? Let's go to the code. Grab that. So we exclude this and add existing item. 19.3, and we've got this one. Okay. So yeah, here is our class vector. Now they've got it on one line here. I prefer to see these on separate lines. I don't know why. It's just what I'm used to. Okay, and strangely, you do see this. That's weird. So this is like a context thing, and usually that appears like in a window that you don't see. You can edit template instructions, and I just never use that. So away it goes. Um, Let me know if you find it useful for anything. It's very much a Visual Studio, a new Visual Studio thing, which I just haven't incorporated into my style. All right, so we got all our old stuff, but everywhere we see double, instead of double, we write T. So LM is a pointer to a T, and operator returns a reference to a T. Why was that a reference again? Oh, that solved a problem where we had to dereference. So if we're going to return a pointer, we had to dereference it, and so this just fixed that, right? Go back and read about that again. Um, and so yeah, everywhere. So yeah, just what I said. Everywhere you see so now when you declare a vector, you need to say what kind it is, right? And so you can have your your vector of doubles, and your vector of ints, and your vector of PD, pointer to double. Okay, that's a fair game object, right? It's a type. So you can have a vector of ints, right? And that all works fine. What's this thing here? All right, so we have our vector template class up here, and down here we have something that's not a template class. It's a vector of characters, I guess. And so, yeah, everywhere you see T, you get replaced by character. And we have a function that takes a vector, reference to a vector of string objects, changes its size according to the size of V, it gets the size of V and it pushes back Nora. Not sure why. Maybe do some other things. I guess, it's just to prove that you can do stuff. I don't think we don't even, we do have a main here, huh? So what does main do? Oh, it just declares these things, right? So all this other stuff is just sort of superfluous here, huh? Do we want to run this thing? I don't think so. Okay, so let's just put it back. All right, save. And I'm going to then add existing item 19.3 .2. This is, both of these have no link, right? So let's skip on to the one with a link, or a link to reality, right? Because they're abstract, right? They're not meant to be run. Maybe we should go read about them. All right, so let's go take a look at 19.3.2. Generic programming, right? So here is where we get this. So like I said, C++ is very flexible. Did I say that? I'm sure I've said it once today. It's a problem with having a long lecture in the morning. You say a bunch of stuff and you're not sure when you've said anything. All right, so generic program. So yeah, C++, very flexible language. It's both high level and low level, right? Which means that, high level in the sense that English words, and low level in the sense is you have direct access to machine memory in ways that many programming languages do not, right? And with that comes responsibility, right? For not creating memory leaks, for not erasing important things, for all sorts of reasons. And then generic programming, so that's sort of a twin concept with object-oriented programming. So let's read what he has to say about generic programming here. Templates are the basis for generic programming. Using templates is what that means, right? So the definition is a bit too simple-minded, though. We should not define fundamental programming concepts in terms of programming language features. Features exist to support programming techniques, not the other way around. As with most popular notions, there are many definitions of generic programming. It's like a generality, right? So a template is a kind of generality. But here's a definition for generic programming. Writing code that works well with a variety of types presented as arguments as long as those argument types meet specific syntactic and semantic requirements. Semantic being, the meaning, and syntactic being the linguistics of it, right, or the grammar. Well, a grammar supports semantics as well, doesn't it? But for it to be syntactically correct means that the parser will be able to parse it without having any syntax errors. So, for example, the elements of a vector must be of a type we can copy by copy construction and copy assignment. In chapters 20 and 21, you will see, I say you because we're not going to get there, but you are invited to read ahead over the summer. I think, as I said, the book supports self-study, which, after all, what is there, right? Self-study. I often get a complaint from students. God, I had to learn that all on my own. Well, hello. Yeah, I would learn it for you if I could. We will see templates that require arithmetic operations on their arguments. Yeah. When what we parameterize is a class, we get a class template. Right, there are also function templates. What is often called a parameterized type or a parameterized class. Right, the parameter being the type, right? When what we parameterize is a function, we get a function template. What is often called a parameterized function, right? So oftentimes, this is like if you get tired of overloading, like, oh, I need to add integers, oh, I need to add doubles, and of course, we don't need to overload the addition operator for integers and doubles. But if you create a rational class, that is, numerator, denominator, rational number, then you have to train the compiler how to add objects of that type. And so you have to overload the addition operator to add those types. When you're printing out objects, oftentimes, well, I'm going to print out a list of this sort of thing or a list of that sort of thing. That's oftentimes a good case where you want to make a template function to print out all kinds of different stuff, right? You just specify the type that you're printing with a template command at the beginning, and everywhere you see the parameter t, which you can call whatever you like, but t is typically what you do call it. For the type of object that you're templating, then that's what you're going to print. Okay. So the form of generic programming relying on explicit template parameters is often called parametric polymorphism. Right. So this is not object-oriented polymorphism. This is parametric polymorphism. Right. So that's that generic versus object-oriented dichotomy at work. In contrast, polymorphism you get from using class hierarchy and virtual functions is called ad hoc polymorphism, and that's called object-oriented programming. Okay, I called it object-oriented polymorphism, but ad hoc, sure, meaning sort of on the fly, right? The reason that both styles of programming are called polymorphism is that each style relies on the programmer to present many versions of a concept by a single interface. Basically means many shapes, right? Referring to the many types of objects you can manipulate through a common interface. All right. So there are several differences between object-oriented programming and generic programming. The most obvious is the choice of a function invoked when you use general programming to determine the compiler at compile time. Oh, determined by the compiler at compile time, whereas the object-oriented programming is not determined until runtime. Right, this is what I was saying earlier, right? That you don't actually create these objects until they're instantiated at runtime with a particular type, right? So when you say vector of int, then at runtime, the compiler creates code to make that type of an object. So when you're pushing back, the compiler will determine the type, the element type for v, and use the appropriate pushback. But for s.draw, the compiler will indirectly call some draw function using its variable table, or vtable, right? This gives object-oriented programming a degree of freedom that generic programming lacks, but leaves the run-of-the-mill generic programming more leaves run-of-the-mill generic programming more regular, easier to understand, and better performing. Hence the ad hoc and the parametric labels. Sum up: generic programs supported by templates relying on compile time resolution. Object-oriented supported by class hierarchies and virtual functions relying on runtime resolution. So the generic programming is compile time resolution? Right, so when you're compiling the code, maybe I said that wrong earlier. When you're compiling the code, it creates, so if you instantiate an object with a template object, it's going to create code that it will refer to for that object, right? Whereas with object-oriented, these things happen at runtime. Okay, sure. So combinations of the two possible are useful. For example, here's a draw all that takes a reference to a vector of point shape pointers. And then so you got a reference to a vector of shape pointers. Here we call the virtual function draw on the basic class shape using a virtual function, right? So that's overriding. That's certainly object-oriented programming. However, we also kept shape pointers in a vector, which is a parameterized type. So we can also use simple generic programming. So, assuming that you have had your fill of philosophy for now, what do people actually use templates for? Unsurpassed flexibility and performance. Sounds like Barnum and Bailey on the back of a wagon. So use templates where performance is essential. Use templates where flexibility and combining information with several types is essential. Okay, so concepts. Okay, so I don't know if we're going to cover this section. See, Bjarne has been pushing this idea of a concept as a new category of object. I don't want to say objects. Go to cppcon.com or the YouTube channel or whatever, and get Strustrup's lecture on concepts. He has several of them, I think. And you'll see where C++ is going to evolve too. We are not done evolving C++. And I think when we are done, not too many versions in the future, we'll have this thing. I think there's already the Boost library has this thing called concepts. All right, so let's see. I don't know, 19.3.3. Do we have any code for that section? This is 19.3.4, right? So we already skipped over it, right? So if we don't have a C++ 14 compiler that supports concepts, so it's already there? Oh, really? I think some of them have them, some of them don't. It's right at the bleeding edge of C++ development. We can specify our requirements in names and comments. Right. So here's a comment that says I have a template of a class vector, and it says requires element of lm. Okay, so the type name. a lem. So this is just instead of t, right? So the compiler doesn't understand our names or read our comments, but being explicit about concepts helps us think about our code. It improves our design in generic code and helps other programmers understand. As we go along, we'll use some more common and useful concepts. Oh boy, yeah. So E can be a lem in a container. Container C. C can hold elements that can be accessed using begin and end. Right, so this is, I think we're getting into that interface between containers, iterators, and algorithms. Okay, so we have this, right, so here, so yeah, you can have more than one template, right, argument. You can have more than one template parameter. So for instance here, equal comparable compares the type T to a U for equality using the comparison operator to get a Boolean result. Predicate, we can use P with an argument of type T to get a Boolean result. Binary predicate with 3 parameters here. We can call P with arguments of type T and U to get a Boolean result. Less comparable? Okay, that's the less than operator, right? So using the less than comparison operator. Less comparable with 3 arguments. We can use L to compare T to a U for less than to get the Boolean result. And a bunch more of these. Okay, so for standard library containers and algorithms, these concepts and many more are specified in excruciating detail here, especially in chapters 20-21. We will use them informally to document our containers and algorithms. Container type and iterator type T have a value type written as value type of template T, which is the element type. All right. Often that value type T is a member type. See vector and list. Okay, in chapter 20. All right, a little peek ahead there. So 19.3.4 is where we are in our code, right? And there is one kind of combination of object-oriented and generic programming that people always try but doesn't work. Attempting to use a container of objects of a derived class as a container of objects of a base class. Okay, so for example, here we've got a vector of shapes. Here we've got a vector of circles, right? So the shape is the base class for a circle object, right? And so if we assign a circle object to a vector of shape, so we're trying to assign the vector of circles to the vector of shapes, right? We get an error because vector of shape is required. If you're going to assign something to a vector of shape, I guess you need a vector of shape. And so here's another one. There's a template. Well, here we're taking a reference to a vector of shapes and trying to pass that to, but why not? After all, I hear you say, I can convert a circle to a shape. Actually, no, you can't. You can't convert a derived class to a base class, especially if it's a pure virtual base class, right? You can convert a pointer to circle to a pointer to shape and a reference to circle to a shape reference, but we deliberately disabled assignment of shapes so that you wouldn't have to wonder what would happen if you put a circle. All right, so so I think we use the equals delete for that, right? We deliberately disabled assignment operator for shapes so that you wouldn't have to wonder what would happen if you put a circle with a radius into a shape variable that doesn't have a radius. What would have happened had we allowed it would have been what is called slicing. That is the class object equivalent to integer truncation, right? So it's like a narrowing error. So we try again using pointers. So okay, so here's a vector of pointer to shapes and a vector of pointers to circles. And we assign that. That's also an error. Again, the type system resists. Why? Consider what f might do. It might push back a new rectangle onto your vector v, which is a vector of pointer to shapes. Obviously, we can put a pointer to a rectangle into a vector of shape pointers. However, if that vector of shape pointers was elsewhere considered to be a vector of circle pointers, someone would get a nasty surprise. In particular, what the compiler accepted, had the compiler accepted the example above, what would a rectangle pointer be doing in a pointer of circles? A vector of circle pointers. Inheritance is a powerful and subtle mechanism, and templates do not implicitly extend its reach. There are ways of using templates to express inheritance, but they are beyond the scope of this book. Yeah, just remember that D is a B does not imply C template of D is a C template of B for an arbitrary template C. And we should value that protection against accidental type violations. All right. So, I don't know, are we seeing that in this code here? Maybe this code doesn't actually correspond to that, because that seems to be more sort of abstract stuff, right? Yeah. Oh, it does say this is an error here, right? No implicit conversion to pointer. So AD is being assigned to pointer to oh, so where is AD defined here? Is it a global variable or something? Let's see. Oh yeah. AD is an array of doubles with 6 elements. So notice that here we have a template class called a struct, I guess, called array. Can I get rid of that? Okay. No, it came back. Stop. Go away. I don't want you. There. Oh. None. Okay. Nope. Okay, and then it wants me to do something. All right, now it's gone. Nope, it's still there. All right, never mind. I'll just ignore it. How are we doing? Oh, it's 4:11. It's time for information. Information science. That's what we used to dial for information. 411. Operator. Yeah, those were the days people did that sort of work. All right, so here's a class that takes 2 template parameters. One is just an int, right? So this is you know, an abstract type, could be anything, but this is a very specific type, right? And our struct array includes a member variable, which is an array of n objects of type T, whatever this is, right? Template. Hold elements in a member array. So rely on default constructors, destructor, and assignment. So the index operator or the subscript operator returns a reference to a T, right? And it takes as a parameter n and returns the nth element of our vector, or the n plus first element, if you will. And we have another version of that here, which is const, right? For those contexts where it needs to be const. And we have a member function data, which returns a pointer to T and returns, yeah, so it gets our data, right? And then we have another overloaded, which returns a const, right? So in the context where we want const stuff, we have that. So it depends on the context as to which one of these 2 data functions is called, right? And we need to provide one with a const modifier so it works in those instances, right? Otherwise we get an error. And we have a size function which returns the size. All right, so here it is, a global array Mr. Global here with array of 256 ints, right? And the 256 is what goes here, right, in the sizing of the array. Looks like we're not allocating it on the heap here, are we? No, we're just having an array. Yeah. So it's not like our vector. It's just an array. Right, so it's got a fixed size then, right? Kind of like arrays have a fixed size, so you can't resize it. And in other words, reserve is not a member function here, and resize is not a member function, right? And so we've got global, we've got an array of double, which is initialized here. Note the initializer list. Do we have that available? Well, yeah. Why? Well, because this is an array, and we can do that with an array, right? And it does have 6 elements, and we specified that. There they are. We have a variable called max, which is a constant, and it's global, and it's set to 124. Okay, so here's a function that creates a local variable, which is one of these array template functions, and it's for characters. However, if we were to try to do that with a variable n, right? So here const is a max is a global const, right? So we can use max in this position, but we can't use n unless you get. I mean, I'm always surprised when it actually works. What? I thought you couldn't use a variable there. Well, I don't know. I guess it sometimes depends upon what compiler you're using or what context you're in. So here we can do this, right? And we can make a backup copy. So we have the assignment operator here, assigning to another local variable, loc2, of the same type, and it's got the same max. And then we can restore it back. And you could do some stuff in between here, right? So he's just sort of saying, here's something you can do. And here's a printout function, which is another template class. And I prefer to see my template on a separate line. I think that's sort of standard behavior, right? So if you're inside the function definition, you get this weird thing. Right, so printout is just doing what you expect, right? And then in main, you can't create a pointer to double and assign it to AD, or assign AD to a pointer to double, because there is no implicit conversion to pointer. Right, AD, what is AD? AD is a template class up here. And it has no implicit conversion to pointer. Right, so it doesn't have a easily accessible memory address like that, right? And then we pass it on to printout. That should work all right. We have a vector of ints, and I guess are we including? Yeah, we've got the vector library here, and we're using the standard for both cout and the vector. All right. So main is taking a. And this is very common for main to take an argument. So this is the number of arguments it's taking, and this is the list of arguments, right? As an array of string pointers. So each argument is a C-style string, and okay, are we actually using that here? I don't think so. But this is a common. We haven't done much of this, right? But you'll see this a lot in the literature. The standard parameters for main. If it's going to take an argument list, that's how you do it typically, right? How many arguments? And here they are. So then we creating queue, which so now we can access right, data returns a pointer to a double, right? Should we look at that again? Yeah, there. Oh, it's pointer to an object of type T, and since what here? AD. What AD is? Sorry, where is it? Here. Yeah, it's doubles, right? Yeah. Um, and so then we can print that out. Shall we see if this runs? Will it blend? No. We've got uninitialized local variable locus right here. Ah, take backup. So it doesn't like that here, huh? And then restore it, huh? So we're saying, yeah, okay. So the assignment operator is not overloaded for. So sometimes you get an implicit value for this, which does the obvious thing, which is assign all the members of the array from one to the members of the array of the other. And since they're the same size, that should work, right? They're both size max. And also set all the member variables of one get assigned to the member variables of the other, and as long as there's a one-to-one correspondence between those, and there is here, it should work. So I think he expected this to work, and yet the Microsoft compiler says nope. We could go to uninitialized. So loc is uninitialized. It is initialized. Oh, I see. It's not initialized here. So what if we give it some values, right? So these are supposed to be doubles. So 1E3, 2, 3E4, something like that. Oh, that's supposed to be a comma there. Okay, so now it's initialized. I guess we don't have default values for these things. I don't know. Yeah, so now it runs, right? And we see, yeah, so we were trying to assign an uninitialized local variable to another variable, and, well, I'm a little bit wondering as to why we're seeing what we're seeing. Oh, I don't want that. What do I want? Is it this one? Oh no, that's window capture. Oh. Oh, I'm sorry. Who is this? Somebody I don't know. There. Not a good time. So yeah, so why are we getting, so I wanted to look at the code, and if I turn on this I get not what I want, right? I'm getting some directory thing here. Didn't I have something with the perhaps I deleted it? Can I? Oh, I think it's because it was associated with a different Visual Studio thing. So, so I got this Visual Studio. Oh, if I'm sorry, I should be looking at output, right? So there's the output with our code. All right, so sorry. Yeah, it gets to be a long day about tea time, and where's my cup of tea? That's the problem. All right, so what do we got? We've got in main, we created AD. Oh, this is a different. What are we looking at here? Oh, this is, yeah, see, this is a different. I see. Okay, so my source code needs to be associated with a different. So can I do that here? I'm going to say properties of the source code, and say yeah, not. Oh, I do want that one actually, don't I? Yeah. Okay, that is the one. I can just say cancel. Right. Okay, so this is some oh, so this some function is not really relevant here, right? It never gets called. Oh, jeez. Okay, so it would, but it did cause an error, right? Because so shall we try calling some function and see what it does? Um, and so we could print out some things here. So we can call print out, right? This is our print function, which is a template function, right? Isn't it? Where's the print? Yeah, it's a template function, right? So that then the name of the parameter is C instead of T, right? But yeah, so it takes a reference to a constant object of type C and walks through and prints them all out. So if I go here under some function, where is it? Here. And after so I could like call it here and call it here and call it here. I think it's VI is not an array though, right? VI is a vector of ints. So can I pass it? So VI doesn't exist here, but can I pass this loc, say? Yeah, seems to be okay with that. And then loc2. Now loc2. Okay. So then restore and print out loc again. Oh, see, loc2 is assigned to, yeah. Okay. And I think we need, okay, it doesn't like that. Oh, it doesn't like the fact that I don't have a semicolon. Expected semicolon. All right, and so now let's go ahead and call some func on n, which n is never used in here, right? Right. The idea is that there's an error. But so yeah, in main we could call some func on an integer n. What integer? I don't know, 5. All right, let's see what happens here. Does this parse? No. Printout identifier not found. So printout is a template function somewhere here. Oh, but it's it's defined after that, right? So let's move its definition up here so that we have access to it, and compile that, which we get then something. I'm not sure what. There's no output now. Oh, okay. Something happened. There's a lot of dead air here. Oh, okay. So we had some. Oh, so it did something here. Should we see why it did what it did? So if we go to main, we see. Yeah, it creates. Oh, well, AD is a global variable, an array of doubles, right? And we access its data function, which returns a pointer to a double, and assign that to Q. And that seems to work all right. We never use that, right? We're just sort of proving that it works. And then we print out AD, which is a global variable. That's fine. I don't know, for some reason we're printing out. So when we call some function of 5, that's what's printing out these weird characters here, right? We got a little phi and a 0, which, well, this is... Oh, I see, because it's an array of characters, not an array of doubles. I guess it's been a long day. Sorry, folks. So this is a... There's not a recording of this, is there? We'll make sure to deep six that. Yeah, so this is what... Oh, dear. Here it is, the end. I think this is what you call ending on a whimper. Can I have a bang? Anybody care to bang? Well, let's see. All right, so it's 4:28, and you've got a few minutes left here. What was do we get through our agenda? Well, no, that meant doing chapter 19, which we're sort of bogged down here in 19.3, 19.3.4. But this is kind of what I do when I read the book is experiment with things and see what's what. That's the best way to and it's the great thing about computer science is it has that aspect of science which is experiment, right? And through experiment, we gain hypotheses about how things work, and we also gain, it's a crucible of truth. If it doesn't work, that's because the compiler or somebody is rejecting it. There's a logic error or a syntax error. Unlike in math, where we can make errors and never know it, which I suppose you can also do in computer science, right? It's not until you ship your software that you get enough beta testing in real time to get a bad review. What should we study prep for the final? What have we covered this semester? Chapter 10 through chapter 19.4? Let's see, what is in 19.4? Let's go to there. So template parameters. Template argument deduction. Yeah, this is a fascinating area of, what is the type of a variable? Can you deduce that, right? And that's that auto. Does he talk about auto here? I don't see auto in there. Generalizing the vector. That's a long section on that with a little warning at the end. Messing with allocators is pretty advanced stuff. Yes, indeed. So A here is an allocator, and that becomes one of the parameters for our vector template. So go ahead and read that on your own, but I guess range checking and exception. So let's say 19.3, that's as far as we got, right? Now the midterm part 2 is mostly on polymorphism, which I guess, that's fair game too. So I'll try to ask some basic questions that kind of cover the waterfront. Try not to be too tricky. Try to offer you, I think there's typically like a 10% ding for having a wrong answer, and you get another shot at it, kind of thing. That's a good question. I don't think we covered chapter 10. It was chapter 11. Shall we go back and review? Chapter 10 was I/O, right? But I think chapter 11 is 2. Yeah. So chapter 11 is just customizing I/O. So all the stuff in chapter 11 assumes the stuff in chapter 10, right? Yeah. So we talked about the void star, right? And stripping off the type of a pointer. So it's just a single byte. And then doing static conversions. And yeah, there was a lot of that. I guess it's got to be like open book, right? I'm not. I guess some of these people are using like Proctor U or something like this, one of these Proctor exams. No, in fact, I would just invite you to try to be as honest as you can about what you know and show what you know. And I would also advise you, if you don't know something, don't expect to, be able to look it up on the fly in a book, right? So, study the book first, and then if you don't know something, well, move on to the next thing, and then come back to that if you have time, right? So I'm thinking more simpler questions rather than a few hard questions. So, and maybe some definitions again. That's always a good question. Yeah, thanks for chapter 11. That's right. Bankruptcy. Well, that's that's a different chapter 11. But I think we're running short on time, and I know some of you have other gigs. This is not your only gig. And so I guess if you have nothing further, I will wish you a pleasant evening and remind you that I should be available for office hours, either by appointment or a regular class time on Monday should be Monday afternoon, huh? Should be available as sort of, let's sort of count on that being. If I go to my calendar, um, do I see anything there? Uh, calendar. Which where is the calendar? I have to go here and see. That's going to be. Uh, yeah, it looks like I had 7A extend further than 7B. Oh, here's 7B, June 1st. Yeah, I sometimes it gets a little sloppy with when does my class end on the calendar, which doesn't really matter for you. But looks like I don't have anything on Monday, the 20th. I think is the no, the Monday the 18th, huh? Yeah. So there's nothing there. So I mean, I have 7A, I guess, the final exam, um, and then for you, I have 7B, the final exam here, which is not listed on my calendar. But yeah, there are a bunch of things that are scheduled that aren't on my calendar. But yeah, I think I'm free. So let's count on having office hours on Monday at 2. Great. Hope to see you then and there. And have a great weekend. Um, right, as the catchphrase goes, stay safe. Don't walk off any planks. And I will see you on the flip side. Ciao for now.